What's up, y'all? Welcome to Chapter 4. This is your boy Bergman here coming to you. Section 4.1, Polynomial Functions. Let's get some vocabulary written down. You can see constant, linear, quadratic, cubic, quartic. Please write these down, the things in green. Just some vocabulary, and I want to give you some examples here. You might recognize a lot of these already as things we've done. This is call this Chapter 2 right here, where you talked about lots of linear things, lots of lines and intersections of lines, and they were like 3x plus 9 at, y equals 3x plus 9. And then the last chapter, Chapter 3, you saw a lot of quadratics, and exponents was 2. Well, the theme for Chapter 4 is going to be bumping up the exponent and see what happens. And so we need some vocabulary to describe that. If you see something with an exponent of 3, then you could call that cubic. Something with an exponent of 4, you call that quadratic. And it keeps on going. We're typically not going to see things higher than 5 or 6 at the very most. But here's some basic vocabulary. And then also on top of that, we can also classify things based on how many terms they have. So if this is you can see if 9x to the fourth is just there's one term, we'll call that a monomial. And two terms, binomial, bi for 2, trinomial, 1, 2, 3, there's 3 of them, quadrinomial, there's 4 of them. Typically not going to see more than that, but it's just some handy vocabulary. And so polynomials are based on this idea of monomials, like just one of them. A binomial has 2 monomials, and a trinomial has 3 monomials. But let's talk, what exactly is a monomial? I'll tell you what, first of all, all of these here are the sums of, or subtractions of monomials. So 9x to the fourth is a monomial, and z squared over 2 is a monomial. Here's what's not a monomial. 3 to the x is not a monomial because it has a variable in the exponent. 6 divided by x, or 6 over x is a fraction. Nope, not a monomial because it has a variable in the denominator. 3x to the negative 2, negative exponent, we're not going to talk about that in Chapter 4. It's not a polynomial. What about exponent of 1.5? Nope, no decimals. And this might be a monomial, but it has 2 variables, and that's just one thing to consider. Often what we're doing is polynomials in just in one variable. Your mystery function, sine of x, that's not a polynomial. And if you have parentheses or it's unsimplified, then that's not a monomial either. You'd have to distribute that to get a monomial. So what exactly is a monomial? If it's just in one variable, like you see, all the ones in blue are a monomial in one variable. It would just look like this: a raised to the x, a times x raised to the n, where a is a real number and n is a whole number. So like we saw here, 9x to the fourth, negative 9y to the third. You can sub out the variable if you want. Instead of x, you could have y or z or whatever. But you've got a number out here in front, a real number times a variable raised to a whole number. Good. And a polynomial is just the sum or difference of monomials. As you can see here, they're all being added or subtracted. We're only going to talk about polynomials in this chapter, and they could have a degree higher than 2, maybe 3 or 4 or 5. The degree is the highest exponent of that polynomial. The leading coefficient is going to be a coefficient of the term with the highest exponent. And leading is a little sometimes misleading because students think it's just the first exponent that they read, and that's not exactly going to be true. You can see here the degree. Let's take a look at 4x to the fifth plus 3x squared. This is a quintic binomial because it has a degree of 5 and there's 2 terms. The leading coefficient is going to be 4, not because we see it first, but because it's attached to the variable that has the highest exponent, that has a degree of 5. Here, the degree is 7, as you can see, and the leading coefficient is 3. And that's because there's a 3 attached to the x to the 7th. Here, 2 minus 5x squared, you might want to, sometimes when you write things, you might want to write them in descending order. Like, if you had the choice to write this, you might choose instead to write negative 5x squared plus 2. That would be in descending exponent order. The degree here is 2 because the highest exponent is 2, and the leading coefficient is negative 5 because that's what's attached to the x squared. The leading coefficient is not 2. The degree here is 0 because that's what we're going to call constants. You can see constant degree 0, and then the leading coefficient would be 2. So end behavior is going to be kind of a new thing. We're going to talk about the end behavior of these polynomials, and it's the behavior of the function as x approaches positive or negative infinity. This really only applies to polynomial, but we've seen this concept before. In other words, it's the trend of the graph as it leaves a zoomed out viewing window. You know, the graphs, as you read them from left or right, they can go up and they can go down, and they can kind of get a little constant and then keep on going up or keep on going down. But eventually, if you have a zoomed out version of your graph, eventually they only go up, and they just keep on going up, and they don't stop going up, or they keep on going down. So the end behavior is going to describe what that happens, how that happens on a graph. We'll see more of that in a second. Polynomial form is going to look like this. It's a function with just polynomials. No parentheses, and it's important for us to know as well. So that's the vocabulary. Let's talk about the domain of polynomials. Domain of polynomials is just the collection of all the x values, and as it always has been, it's the collection of all the x values. And for polynomials in one variable, this is always going to be all real numbers. There's no if you had square roots or you had variables in the denominator, then you'd be able to say, wait a minute, the domain isn't all real numbers, and it needs to get restricted, but for the domain is always going to be all real numbers for polynomials. The range is going to be the collection of all the y values, and that can change all the time. All right, let's take a look. So if we were to graph 5x to the fourth plus 1, you notice that this is a zoomed out version. Eventually, as x goes to negative infinity, as you get lower and lower x values, this is going to keep on going up. And the same thing over here. As x gets larger and larger, the y values get higher and higher. And so we can call that behavior up, up. Notice also the degree is 4, which happens to be an even number, and the leading coefficient is 5, which is a positive number. It turns out if the degree is even and the leading coefficient is positive, then it's always going to be up, up. So if we change this to 6x to the 6th, it would also be up, up. Let's take a look at this. If the degree here is 2, that happens to be even, and the leading coefficient is negative 2, you can see one big change is that this is pointing downwards. It's opening up downwards. We're going to call this down, down end behavior, because as x goes to negative infinity, the y values go to negative infinity as well. Here, the degree is 7, and it's going to be going, and the leading coefficient, it's not written, but there's always an imaginary 1 in front of all variables. And so we're going to call this down, up end behavior. And then it's just the arrows. You can see this is pointing down and this is pointing up. Here, the degree is 3, not because of the first term that's written, but the second term that's kind of written out of order a little bit. That's okay. The degree is 3, it's odd, which is an odd number. The leading coefficient is negative 4, and we note that that's negative. And so the end behavior is going to be up. We're going to call up, down. Here's a summary of what's going on. And you can see here, whatever this little gray squiggle just means it could go up. In the middle of the polynomial, it could go up, it could go down, it could approach kind of the saddle and then keep on going up again. But if the leading coefficient is positive and the degree is even, like the graph of y equals x squared, then it's going to be up, up. Like the graph of y equals x to the fourth, or y equals x to the sixth, or y equals 3x to the sixth. All these graphs are going to have up, up end behavior. If you switch that to a leading coefficient of positive and an odd degree, like y equals x to the first, or y equals x to the third, or y equals x to the fifth, then it's going to have down, up end behavior. You notice the down arrow, the up arrow here. And so if the leading coefficient is negative, this whole thing gets flipped. It used to be up, up, but if it just has an even degree, it'll be down, down. Notice the negative out in front. That's a negative. The transformation would be a vertical dilation of -1. So everything gets flipped downward. And over here, what used to be down, up, on the graph of y equals x is now y equals -x, and it gets flipped to up, down. This is a handy little chart to have memorized. And when the time comes, I know we'll practice it enough that eventually memorizing it will be a bit easier. So we had an in the previous page we had polynomial form, and that's just, you see all the polynomials being added there. There's no parentheses. The exact opposite of that is going to be factored form. And you can see everything is factored. Lots of parentheses and one giant term, very low exponents. Ideally, the exponent on inside each of these is 1 because they're easy to solve. And if you want to find solutions, or if you want to find x-intercepts, or if you want to find zeros of a function, then factored form is definitely the way to go. And so converting it completely to factored form is the best. So if you wanted to solve something like this, you know that the zero product property says that if there's multiplication here and two things are multiplied equals 0, then each of them individually could equal 0. So this becomes 2u minus 12 equals 0. That's from this first part. Or just 2u equals 12 or u equals 6. That's the first solution. And then the second part would be u squared plus 9u plus 18 equals 0. We get to factor here if it's a quadratic, so we're going to split the middle. Let's see, we need two numbers that multiply up to 18 and add up to 9. That would be 6 and 3. I didn't write out the list. Sometimes it's helpful to write out the list of factors, but I think I ran out of room. Finding the greatest common factor of the first two terms would be u, the variable u, and then what would you need to distribute? What would you need inside parentheses to distribute here? You would need u plus 6, because u times u is u squared, and u times 6 is 6u. And then here, the greatest common factor, there's no variable in 18, so it's only going to be a number, 3. And 3u plus 18, if you have a 3 on the outside, what will you need on the inside to distribute to get to 3u plus 18? It'd have to be u plus 6, because 3 times u is 3u, and 3 times 6 is 18. Notice we get confirmation we did this right, because we get the u plus 6 written twice. And so we're going to take the greatest common factor of both of those and get u plus 3 and u plus 6 equals 0. The order of these doesn't really matter very much. And the order of the 6 and the 3 here also doesn't matter very much. Anyway, we're going to split these up, zero product property again, to get u plus 3 equals 0, or u plus 6 equals 0, and then we've got our solutions. Here, this is almost in completely factored form, except that I think we can factor the inside. 3v gives us a solution of 0. 5v plus 5 over here gives us a solution of -1. You can see we're splitting these up along along the multiplication here. But v squared minus 7v plus 12, I think we're going to have to factor that. Give me two numbers that multiply up to positive 12 and add up to -7. They both have to be negative. -3 times -4 is positive 12, and -3 minus -4 is -7. So there we go. Greatest common factor of the first two terms is v, and then we get v minus 3 over here. Greatest common factor of the second two terms would be -4, and we get v minus 3 over here. V minus 3 gets written twice, so that's why we put it here, and v minus 4 gets written over here because it's v minus 4, it's what's left. And then we get these two, and then collecting 0, 4, 3, and -1, and that's the solution set. Notice there's like 1, 2, 3, 4. There's 4 different solutions. That's going to be more normal over here in chapter 4, because why can't I scroll over very easily? Because we're just allowing for higher exponents. Find the zeros. Here's a function. We want to know what inputs will produce an output of 0. So if we want an output of 0, just set it equal to 0. And once we set it equal to 0, we know how to solve it. So we're going to split this up into -2x equals 0, and x squared minus 16 equals 0. Notice we can add 16 to both sides and take the square root of both sides. And anytime we're taking the square root of both sides, we can get plus or minus 4. So the solutions are written here, 0, comma, plus or minus, and then I want you to figure out what's underneath the red dot. All right, take care. That was your introduction to chapter 4, polynomial functions. I'll see you in class.